is a friction simulation in Java using two boxes, each having their own applied force, speeds, and masses. Friction is a resistive force that opposes motion between two surfaces in contact, and in this simulation, it is between the box base and the floor. In our world, the use of friction occurs every day. For example, when you walk, your foot pushes you backward on the ground. Static friction, which we will talk about later in this video, pushes you forward. Without friction, you would slip like on ice. Another example is driving a car. Tires grip the road to move forward. Brakes use friction to stop the car. Turning also depends on friction. Even when you write something with a pencil, friction between pencil and paper leaves marks. Without friction, writing would not be possible. Now that we have talked about some examples of friction in a day-to-day basis and the general definition of it, now we will be discussing about the two types of friction. The first one being static friction. Static friction is the force that keeps an object at rest when a force tries to move it. It acts between two surfaces in contact along the surface opposite to the direction of the applied force. Overall, a simple definition of static friction is the force that prevents motion from starting. Static friction changes depending on how hard you push up to a maximum value, and the general formula of this is F of S is less than equal to mu S times N, where Fs is static friction, mu S is the coefficient of static friction, and N is the normal force acting upwards. We also have a thing called the maximum static friction, and the general formula of this is Fs max is equal to mu S times N, where Fs max is the maximum static force, mu S is the coefficient of static friction, and N is again the normal force acting upwards. If the applied force becomes larger than this value, the object starts moving and kinetic friction begins its process. Speaking of kinetic friction, that dives into our second type of frictional force, kinetic friction. Kinetic friction, also called sliding friction, is the force that opposes motion when two surfaces are already moving against each other. It acts between surfaces in contact, parallel to the surface, opposite to the direction of motion. A simple definition of this force is the force that slows down a moving object when it slides over a surface. The formula for kinetic friction is Fk is equal to mu k times N, where Fk is equal to the kinetic frictional force, and mu k is equal to the coefficient of kinetic friction, and N is again the normal force acting upwards. Friction was first studied by Leonardo da Vinci, an Italian polymath artist and engineer who observed in the 1400s that friction depends on the weight of an object and not the contact area. Later, Guillaume Amontons, a French physicist, rediscovered the laws in 1699 and showed that friction is proportional to the normal force, forming what we now call Amontons' law. Finally, Charles-Augustin de Coulomb, a French physicist and engineer, expanded the work by distinguishing static and kinetic friction and developing the famous equation as we know today, F equals mu times N. In this simulation, I used many equations, starting off with gravity, which is equal to m times g. M is 5 kilograms, which is the mass of the object, and g is the gravitational constant on Earth, which is 9.8 meters per second squared. Solving for Fg, all we do is 5 times 9.8, which gives me 49 newtons. So therefore, the force of gravity acting on the object is 49 newtons. Second, we have the normal force. Solving for this is pretty easy because the normal force is equal to the force of gravity. So therefore, we do 5 times 9.8, which gives me 49 newtons. Third, we have the maximum static friction. The maximum static friction is equal to mu s times Fn, where mu s is the coefficient of static friction, Fn is the normal force. Solving for maximum static friction, we do 0.5 times 49 newtons, which gives me 24.5 newtons. Since the applied force, which is 40 newtons, is greater than this maximum static friction of 24.5 newtons, the box starts moving. Fourth is kinetic friction. Fk is equal to mu k times Fn, where Fk is the kinetic frictional force, mu k is the coefficient of kinetic friction, and Fn is the normal force. Solving for Fk, we do 0.3 times 49 newtons, which gives me 14.7 newtons as my final answer. Fifth, we have the net horizontal force, which is equal to F applied minus Fk, where F applied is 40 newtons and Fk is 14.7 newtons. Solving for F net x, we take the difference of the two. 40 newtons minus 14.7 newtons gives me the final answer of 25.3 newtons. Lastly, we have the acceleration. Using Newton's second law, A is equal to F net divided by m. To solve for A, we do 25.3 newtons divided by 5 kilograms, which gives me the final answer of A to be 5.06 meters per second squared, which represents our acceleration. Now that we have got the knowledge part out of the way, now what was left is coding it. First, I declared a JFrame and variables. For the JFrame, I named it friction box simulation, and for the variables, I declared variables called G, the mass of the two boxes, applied force, Vx, which is the velocity in the x direction for box 1, Vx2, which is the velocity for the second box, coefficient of static friction, coefficient of kinetic friction, dx, which is the starting position in the x direction for box 1. Next, I used all of the physics equations that we discussed and plugged them in. Step 3 was determining friction and net force. This code checks how friction acts based on applied force. No force means no motion, small force balanced by static friction, and large force causes motion with kinetic friction and a net force. Fourth, I declared J components. For the floors in the simulation, I put them as JPanels, but for the boxes, I put them as image icons. Fifth, I initialized a timer. This code runs when the net force is greater than static friction, meaning the object starts moving. A timer updates their motion every 0.01 seconds. Velocity decreases over time due to kinetic friction, and distance increases based on velocity. If either box hits the screen boundaries, direction reverses. The positions are then updated on the screen using swing. Lastly, step 6 is window setup. This code sets up the window by defining its size, background, and layout, and then adds panels and boxes and makes the frame visible. Now I wanted to play around with the velocities in the simulation. So first I changed the velocity of box 1 to be 100 meters per second. Then I also changed the velocity of box 2 to be 100 meters per second, same as box 1. Then I ran the simulation and here are the results. As we can see, the boxes are moving way quicker and making more collisions with the walls compared to 20 meters per second, which we had set up regularly in the simulation. Pretty cool seeing how the boxes are moving with this speed at such a fast rate. Okay, next I wanted to experiment with the masses of the boxes. So I set them to be 8 kg, 3 more kg than what we had before. And here are the results. As we can see, the boxes are coming to rest at a much more quicker rate compared to the masses of the 5 kilograms, which we had initially set up in this simulation. And that is the simulation of friction in Java. I hope you found this video helpful. The source code will be posted in my GitHub attached to my channel description. Please make sure to subscribe if you want to see more coding videos. The next project I will be making is projectile motion simulation in Java. So I hope to see you guys all then. Bye bye and stay safe.